Law number 2. So he said that the planets move through their elliptical orbits in such a manner as to sweep out equal areas in equal times. So imagine a line that extends from the sun to the planet. As the planet moves in its orbit, the line moves with it and sweeps out an area. In the same amount of time at any other position in the planet's orbit, the planet will again sweep out in the same area. So that's kind of a lot of jargon. So let's draw a picture to help us visualize this. So again, still on page 270, we can draw that picture there. So draw your sun, and then really around it, draw the elliptical pattern, say of Earth going around. And then here it showed you 2 shaded spots that it broke it down into the area. So if we think about it, the Earth is orbiting around the sun. But so if we break it down into different spots, so like this spot here, draw your lines out. This would be, in the book it says that would be like area 2. And say we compare another space or area, but it covers a lot more time. Or sorry, it's in the same time. So even though these spots are very different, it's still covering that same area in the same amount of time. Well, how can that be possible? What would the planet need to do in order to cover that same area in the same amount of time? So what did you say? Speed up, yeah. So the planets will have a different speed of their ellipse depending on where they are on their elliptical orbit. So this is due to the fact that the planets move at different speeds. During its orbit, depending on its radius. So its radius meaning like how far away, really, from that object that's emitting that gravitational strength. Okay? If it is far away, so the planet here at area 2, this is a much larger radius. It's farther away from that source of gravitational strength, so it's slower moving. Therefore, you should write this down, therefore it travels less distance in same time. Here, if our planet is on the same, basically quite the opposite side, the planet is much closer to the object that's emitting the gravitational field strength. So it's going to have this is a smaller radius. So it will be faster moving. Therefore, travels more distance in same time. Okay, so I'm just going to show you a small YouTube clip that helps to illustrate this.
orbiting a star. So here my planet is orbiting a star at some initial time. We'll call it time 0. I'm going to draw a line between the two objects. This is the line that we are going to say sweeps out area. As this object starts to orbit around, this line will continue to move up and to the left a little bit as it circles. At some later time, we're going to give it an arbitrary 1 at the moment. We're going to say that the area that was swept out by that moving line is indicated by this dark purple region to go from 0 to 1. If I allow an equal time interval to pass, so if we wanted to say that that was 1 month of time, if I allow 1 additional month to go by, I'm going to sweep out some additional area. This time I'm showing that to be light purple. Kepler's second law tells us that the area swept out for both of these time intervals, the first time interval and the second time interval, must be equal. That's to say area swept out at a constant rate for a constant time. I can continue the pattern. Let's see what happens if we go 1 additional month. I can sweep out some quantity of equal area. These things are not quite triangles, although they're pretty close to that. I can keep going. Here we are at month 4, month 5, 6, 7, 8. Again, every different region that I've swept out here, we say must be the same area as any of the other regions because we're moving at constant time intervals. What's important to notice is that look how far the planet travels from, say, 0 to 1 compared to how far it travels in the same time interval, but to go from, say, 3 to 4. It travels a much further distance from 3 to 4. The planet will actually start to travel faster as it gets closer to the central massive object. This is the only way that the area that's swept out can remain constant for a constant time interval. This is really best seen by, again, going to...
Okay. All right, let's do law 3 next then. So again, that just kind of shows you